So derivatives are a fantastic mathematical operation we use all the time in physics, and in this class in particular, we're going to be using power derivatives, so I will show you how to do one of those. Say you have something y, some variable y, and it depends on time. So I'm going to write t in parentheses right here underneath y, so to remind myself that when t changes, y is going to change. And here's the equation for it. It'll be some number, I'm just going to call that b, multiplied by t, and t will be to a power n, and then maybe we'll add a constant. Now if I want to know what the derivative of y is with respect to t, which we write like this, dy dt, here's what I do mathematically. The b doesn't change, it just stays right in front like that. And now we take the exponent of t, which is n, and we multiply by that, and then we have t, and we subtract 1 from its exponent. So it's t to the n minus 1 now. And then c is a constant. So constants, by definition, are constant. That is, they don't change. So when we take a derivative, which is essentially a change, that becomes 0. There is no change in this constant as time changes. So that is the derivative of this equation y. Let's try out an example with some actual numbers. Say y is equal to 4 times t to the second plus 3. Then, if we want to know the derivative of y with respect to time, the 4, that's like the b, that just stays out in front. The power of t is 2, so that's the n, so we multiply by 2, and then we have t to its power minus 1, so that's t to the 2 minus 1, and then 3 is a constant, just like c was here, so it's equal to 0. So then if we clean this up, we'll have the derivative equal to 4 times 2, that's 8, and then t to the 2 minus 1, that's t to the first power. And we could write a 1 here, but usually we just leave it to be understood. And then plus 0. Again, we could keep plus 0, but there's no real reason to write that. So this, 8 times t, is the derivative of this equation here. Let's do another example. Say y is equal to 4 times t to the third plus 6 times t plus 2 over t to the fourth, let's say. Okay, so now we're going to take the derivative of this equation y with respect to t. So the 4, just like the b, it stays. T, this t is raised to the third power, so that's its n, so we multiply by it and then subtract 1 from it in the exponent of t, and then 6, so it's like the b, it stays. T, well, it doesn't have a power explicit, but when it doesn't have an explicit power, that means the power is 1, so n is 1 for this t. So we multiply by 1, and we do t to the 1 minus 1 here, following these rules, and then this guy, that's a little confusing, so let's rewrite it so it's less confusing. That is 2, and then 1 over t to the fourth is the same thing as t to the negative 4. So this fraction is exactly the same thing as this multiplication. So then, now we know how to take the derivative because it looks like this. So the 2 stays there, it's just like the b. The power, that's negative 4. And then we do t to its exponent, negative 4 minus 1. Now we're ready to simplify this. 4 times 3, that's 12. T to the 3 minus 1, so that's t to the second power. 6 times 1, that's 6. T to the 1 minus 1, that's t to the 0th power. 2 times negative 4, that's negative 8. And then t to the negative 4 minus 1, that's t to the negative 5th. And we can clean this up even some more. 12 times t squared plus 6 times t to the 0. Well, anything to the 0th power is just 1. So this is actually just 6 times 1, or just 6. And then here we have t to a negative power. So we can basically undo what we did here and go back to a fraction. So that's negative 8 divided by t to the 5th. And so this guy is the derivative of this equation up here. And that's how you do power derivatives.